So welcome to the second to last talk this morning, Wednesday, June 9, iRODS UGM2021. This is Peter Braam from ThinkParQ. He's going to talk about large file system indexing and iRODS. Peter, you've got the floor.
Thank you. So I work in the area of very large file systems. Perhaps I should give you just a few seconds of introduction. I started with academic projects and then developed Lustre in the early 2000s and a number of related systems. And I joined ThinkParQ about a year ago to work on BGFS. And no surprise, the background of this talk is that some of our larger users wanted to use iRODS, and they have truly many files and very fast file systems. So their scans to get things into the iRODS databases took weeks. And on top of that, BGFS had no persistent change log. It still doesn't and probably won't. It has a socket with events, but you can't drop the connection. So the question came up, what should we do? And there were quite a lot of related questions, like could we easily find the files that haven't been accessed and the files in subdirectories or the files on storage devices? These are the typical questions. These problems aren't really new. A few years ago, I worked for a little while on a concept called campaign storage. It was explored and initiated by Los Alamos. And the campaign storage file systems were even larger than the typical cluster file systems. I'll show you a picture in a moment because they are sort of some staging space between archives and the compute file systems. And those days we explored two indexing systems. One was created by Lanel and called GUFI, the Grand Unified File Index. And I described something else, and it was prototyped but not really publicly released, which was called a hierarchical subtree index. And I want to give you a flavor of these things because I think they provide a possible way to get a lot of stuff managed by mature systems like iRODS, eliminating some of the bottlenecks between the impedance bottleneck that there is between a super fast file system and something that is really targeting somewhat different kind of infrastructure. So both of these indexes, by the way, I never know whether you say indices, indexes, or whether there is even another plural for this, but let's just call it indexes maybe. They are a collection of databases, and they have one database for each directory in the file tree. And so you can store these databases embedded in the file tree or outside the file tree. There's actually an advantage to each that I'll explain in a minute. But one of the nice things is that with a scalable metadata server, these databases can be populated in parallel and they can scale. So here's a picture of what campaign storage is supposed to do. So campaign storage refers to an intermediate stage, you could say, for data. It's not quite on tape yet, but it is moving out of compute or machine learning clusters into some longer term storage for what is the duration of this particular campaign of effort. And so the campaign storage is typically used for months to a couple of years. And it is very much subject to wanting to have data management, finding the important data files that need to be archived permanently, getting rid of stuff we don't need. And campaign storage separated the metadata and object data even further than parallel file systems have done, and the crawling took even longer there. And I think that is what caused a lot of thinking about this. So tools that have been used in the industry, Robinhood in particular, tends not to scale to these kind of file systems on the order of 100 petabytes with billions of files. Nevertheless, particularly something like iRODS has the workflow capability that is very successful. So we wanted to find a bridge. So the perspective for these indexes is, let's create a faster, scalable feed for iRODS. Independently, you could look at this as a basic, and I really mean basic, not something that is 100% accurate, but a reasonable initial solution for archiving, creating space where the files that are large, perhaps managing projects and users. So what is used in the subtree of the file system, what is stored on particular devices or in pools of devices. Yeah, these kind of basic storage questions are something that you can, in a first approximation, address with an index. Let me tell you a little bit about GUFI first, and then about the other hierarchical index. So the GUFI is actually a project on GitHub, so you can look at it. I don't think there are so many users. It's pretty well engineered, I think. Los Alamos has a very good team of storage engineers, and they spend some good time on it. And on the other hand, I also think it needs a lot more development to be really a good product. So how does GUFI really work? So GUFI looks at one of these very large file trees and says, in each directory, I'm going to place a little database. I think typically they use SQLite for the database, but it could be anything really. And GUFI has 3 tables. So one is called the entry table, that has a record for every inode in that directory. So it's actually like the directory, but it's also a little bit different because all the information is in one database record, and these database records are in one database table. So it is quite different from the layout that you would see in a file system directory where inodes can actually be scattered among multiple servers. Then there's a directory summary that I think is quite similar to the hierarchical summary that I mentioned later. And so the sort of thing that is in these summaries is the number of files in the subtree, the minimum file size that you find there, the maximum file size, and perhaps a number of other attributes. Finally, there's a tree summary. It appears not to be used very much in GUFI. So GUFI scans the entire file system to populate these databases. And like I said before, you can put these databases simply as a database file in each directory, or you can create a mirrored directory tree, perhaps on a single data management server that has maybe some NVMe fast drives or something like that. The in-tree storage has one big advantage, namely the databases are accessible to anyone who has the file system accessible, and users can do searches. Yeah, and these user searches can be quite helpful to them. For example, they can create lists of files that are very painful to create on large distributed file systems. If you do, for example, even a simple thing like give me the summary of the bytes used, du minus s in a subtree on a distributed file system, you're not going to be happy. Yeah, these file systems are fast, but they're not so good to crawl millions and millions of files. You can also make a mirror directory tree, typically used perhaps by a data management server, because that tree may not be shared, that server may not be running a shared file system where it stores its databases. So it's typically smaller amount of data, because also all the file inodes don't have to be stored in that tree. You just have the directories with these tables that we're adding, that GUFI is adding. So GUFI is quite easy to use. So the sort of the norm of things is perhaps that a record has a size of 1 kilobyte. So 1 billion files would consume 1 terabyte of data. So that works very well with a set of NVMe drives these days. And file systems with billions of files are still considered on the large side. And you could, of course, build a file server with 100 terabytes of data or something like that. The kind of queries that you can throw at GUFI are things like, find the files larger than 1 gigabyte in a subtree, find files not accessed since a particular time, find files that have been modified before and not accessed after. So these are the sort of things that you would typically throw the find utility at. It would run forever in a very large file system. And this thing spits these results out pretty quickly, like 100 times faster. And I think one of the reasons that it can do some things faster is actually the tree structure of these indexes, because you may, from the tree summary, see, well, I don't have to go down a particular subtree because there is no very old file in it, or there is nothing very recent in it. So the avoidance of descent in a particular subtree is, I think, something that is responsible for accelerating the searches quite a lot. Also, like I tried to mention earlier, saying it in different words, there are no remote procedure calls. There is a lot of data locality in the tables. So this goes quite well. The administrative commands for this database are also very simple. You can create an index, update an index, give some little statistics. So the sort of thing that I think would be even more valuable are the queries that I've shown here on the right. Find the kind of files that are in a particular storage pool. So these use layout information that tends to be quite specific for file systems. The encoding of which servers are used to store a part of the file, like a stripe of the file, are encoded by all parallel file systems somewhat differently. And there's sadly, no uniform interface to this. But you get the gist here. How do you find the files that are on a particular device? Perhaps people want to migrate these files off when the device is old. Let's see. Good. Now, the second index I want to briefly mention is a different one. So this is a similar organization. It has, again, one little database for every directory. But here we only have subtree information. And on top of that, only specific types of information. So for example, the number of files in the subtree is something that you could store. So I call this a histogram. And each of the quantities that you record in the histogram corresponds to one of these search criteria that match a file. So it's some kind of predicate. So the number of files is one, the bytes consumed, but you can actually do quite a lot of different predicates that have usefulness in different situations. So for example, the number of files bigger than something or smaller than something, or owned by a particular user or group, or touching a particular device. So you might say, what is really special about these bars in your histogram? What's different from a general table? So the difference is that they have an additive property. So the number of files that you want to record for a directory is equal to the number of files in that directory plus what you've recorded for all the subdirectories. So there's a little formula that says, if you know the number of elements in your directory and then what happens in the subtrees, you can just add it up and get it for the parent. So that property is what is called a Merkle tree. And there are many different kinds of Merkle trees properties. So Git uses this, and checksumming in ZFS, for example, uses this. And the idea is always that a property of a particular subtree is expressed in properties of all children. And this property makes a number of things very, very easy. So for example, if you move a directory away from a subtree, these particular quantities that are in the histogram are very easy to adjust, because you simply subtract them when you take that directory away from a particular directory. When you move it to some other place, you subtract these histogram bar quantities and you add them in for the other subtree. Secondly, you can propagate these changes in this data really quite quickly, because all you have to do is update a number of parent directories. And so, you can consider different timescales at which you do this. I think it's actually possible to do this real time on all updates in the file system, perhaps on all modifying updates in the file system. But you could also do it based on snapshots and change logs. Yeah, and here with these particular bars, you need very little information to make the updates. So different organization. This one is even more focused on guiding the searches into a subtree. Yeah, they will say, there are a lot of big files here. I need to create some space. This is a good candidate to go further into. Yeah, and another subtree may have no large files, so you can skip it. So it changes whole file system scans into logarithmic scans. Good. So let me summarize a few small things here that we've talked about. So, the origin and the problems that we want to address really are, things like happy high-performance compute archive users. I've never met a happy archive user. Yeah, everybody is somewhat miserable, I think, with their solutions. Second thing is, indexing must scale with the file system capabilities. Yeah, and it is to some degree somewhat unrealistic to say, let's try to build a database that can be as fast as a very large scalable parallel file system. That's really not going to happen. And things like adding persistent change logs, nice, so sure, then you can, take your time processing the change log. Unfortunately, by introducing a persistent change log, you've also just slowed your parallel file system down by a factor 2. Yeah, and I think that this is what was driving the study of these indexes. And, I think they stand some hope as a tool that can solve simple problems in a basic way, or provide a new way of feeding into a mature system like iRODS. Perhaps it's interesting to mention to you that the Apple file system that was released maybe 3-4 years ago, it replaced, was it called HFS Plus or something like that on Apple's computers? I think it's now the default file system for everything. It actually implements similar subtree information. And I don't know exactly about the implementation details, but the ideas are identical to what these indexes were doing. The indexes, by the way, go back some 20 years. I heard that some graduate students were working on this at Carnegie Mellon in the early 1990s or something like that. Just one other thing. So I work for ThinkParQ, and we maintain this BGFS parallel file system. It's one of several parallel file systems out there. Lustre, GPFS, or Spectrum Scale, maybe the most common, but it has quite a reasonable user base, BGFS. We have actually quite a few customers with more than 1 billion files. I don't know what the biggest one is. And these customers actually come back all the time about these sort of problems. We are going to provide an index and data moving tool based on these principles, and we will be releasing that first sort of preview version in the next few months. I wrote a blog post that I should perhaps include a link, but it's pretty easy to find, I think, in January of this year, where I show, how can you do somewhat more tight integrations with the file systems. I think these projects are longer term, maybe, but in the short term, I think we can maybe build a good feeding tool for iRODS and also solve some data management tools, data management problems. I think, thank you very much. That is all I have to tell you. And I'm very thankful that I could present this here.
Thank you very much. This is a great insight, and it's nice to be able to step back sometimes and look at, these bigger technologies from, without kind of being in the weeds sometimes. We do have one question from John Constable. Says, if it isn't impolite, has GUFI been tried on other HPC file systems such as Lustre? I mean, do we have comparative information about these things?
I think it has actually not been used on Lustre, but it has been used very extensively on GPFS. So for one reason or another, Los Alamos built campaign storage within a group of GPFS file systems. So they had like 4 or 5 of these file systems to manage the metadata, and then the objects were actually stored in different ways. So they had all kinds of objects. Eventually, they developed a ZFS object store. So it was kind of an ad hoc file system construction. The whole thing was a user library, all a bit technical. But so GUFI was, I think, tried quite extensively on GPFS by Los Alamos. Also, I know that those developers, they were talking to me all the time. We like to run it on our Mac, to just find our own files back. So we've been running it on BGFS, but I don't know about Lustre.
Okay. And then we have another question that says, wouldn't this be more practical on the VFS layer or like iNotify? And I know that, in a parallel file system, iNotify is overwhelmed.
Yeah, but iNotify would be overwhelmed, but not if you were to do it perhaps on a per node basis. Yeah, so you could get some distributed changelog, but that's very, very difficult to aggregate. Also, believe it or not, I've worked on so many file systems and I've slowly become very intimidated by building file system changes. iNotify also suffers from the problem that the event socket had. Namely, if you disconnect from iNotify, there's no persistent record. Yeah, so how do you resume that?
That's right.
Yeah, my own feeling is that really,
oh no, I think we've lost. I think you might have frozen. Peter,
shots and efficient change logs. Yeah, like, sorry, did you miss anything? Or
yes, we missed a couple sentences there. You froze for a second.
Okay, I'm still alive. I didn't freeze. I'm actually in a very warm place. I was saying that I am hopeful that the sort of enterprise strategy that NetApp Waffle really initiated in the 1990s of having these snapshots and change logs between them, that is a reasonable mechanism to create feeds and process them somewhat later. I'm actually very surprised by the slow uptake of these mechanisms that are now available in ZFS, and that could be influencing all kinds of things from backups to feeding into iRODS and so on. Apparently, it's not so easy, to do that. Is my conclusion.
Yeah, we have not spending as much time as you. Obviously, we came to a similar conclusion that the only way to do this is through some persistent change log, but obviously that's hard, and it's not reasonable for just out of the box for parallel file systems. It's you've introduced a bottleneck back in the system.
Yes. Mm-hmm.
Let's see, I think, does anyone else have any questions? We've got a couple more minutes if we want to use it. Otherwise, thank you so much. This has been great. And yeah, we look forward to seeing what's coming out of ThinkParQ. And we'd love to have you in the room as we figure out how to make this similar for the sandbox that is iRODS.
Very good. I hope to be back.
Very good.
Thank you very much.
Appreciate it.